Welcome back to the deep dive. Today, we are undertaking, well, a pretty critical analysis of one of the deepest conceptual paradoxes in classical physics. We're talking about the very nature of mass.
That's right. We're exploring sources that really challenge the traditional sort of purely mechanical definition of a particle. The big question is, does mass fundamentally originate from electromagnetic fields? Is it all just fields?
That's our mission for today, then, tracing this intellectual struggle to define the mass of fundamental particles. The electron is the classic example here.
Exactly. This deep dive is really about uncovering the specific, almost agonizing conceptual failures, the problems that made it absolutely necessary for physics to, well, move beyond classical electrodynamics.
Okay, so let's jump right into the first big conceptual crisis. It starts when we try to calculate the self-energy of a charged particle. Classical physics often models a particle with charge, let's call it Q, as a tiny, uniformly charged sphere. And it has some radius, A.
Right, little ball of charge. The problem pops up when we calculate the total electric field energy, that's 1 roto, stored in the fields around this charge. Maxwell's theory gives us a clear rule. The energy density, how much energy is packed into a bit of space, is proportional to the square of the electric field intensity, E squared.
Okay, E squared. But what's really fascinating, or maybe troubling, is what happens when you try to integrate that energy density. You sum it up over all the space surrounding the particle, and the total self-energy you get, one next little text selection, it turns out to be mathematically proportional to 1 over A, 1 over the radius.
And this is the exact moment classical physics just breaks. Because if that particle, say the electron, is truly fundamental, truly a point.
Then its radius A has to go to 0.
Exactly. But look at the math. If A goes to 0, 1 over A goes.
To infinity. The calculated electromagnetic energy just shoots straight up to infinity.
We're immediately faced with a complete absurdity. Classical theory predicts that a fundamental point charge must contain an infinite amount of energy just to exist.
Right. That infinite self-energy, right at the starting gate, tells us something is deeply wrong. The simple picture of a rigid, charged point particle. It just doesn't work. It's not mathematically or physically consistent within classical electrodynamics.
So this failure basically forces us, maybe reluctantly, to consider the charged object as having some tiny but finite physical size A, even though experiments, strongly suggest it is point-like.
But okay, even if we accept a finite size for now, the theory quickly throws up the next hurdle, this idea of electromagnetic contribution to inertia.
Right. Let's assume we have our charged sphere of radius A, and now we set it moving at a constant velocity v. It turns out the particle's fields, they don't just carry energy, they also carry momentum.
Because it's moving,
Yeah.
the fields change.
Yes, precisely. Because the charge is moving, the electric field E and the magnetic field B it creates, they kind of get distorted. They stay symmetric along the direction of motion, sure, but they get sort of squashed or asymmetric, perpendicular to the motion. And when you calculate the total momentum, P, stored in these moving fields, you find that P is directly proportional to the velocity, V.
P proportional to V, but wait, that relationship, that's exactly the definition of inertia, isn't it? Momentum equals mass times velocity.
Exactly. The electromagnetic field itself acts as if it has mass. So we define this coefficient, the thing linking P and V, as the electromagnetic mass. Let's call it mass delta.
Okay, so the field has its own inertia. And when you actually do the calculation, what do you find for this mass selection?
The result is mass select equals 2/3 times the electromagnetic energy divided by c squared. So 2/3.
2/3. Okay, hold that thought. But initially, this must have seemed incredibly promising for classical physicists, right?
Oh, absolutely. It suggested that maybe the total observed mass of a particle, the mass we measure, might just be the sum of its, let's say, mechanical mass and this new electromagnetic mass.
And the big hope, the ambition was, what if all mass is electromagnetic? What if that mechanical part, Mottram sex, is actually 0? The electron's entire mass is just its own field energy.
That was the dream.
Yeah.
To give this idea some physical scale, physicists define something called the classical electron radius, usually written $2. Now, this isn't a radius somebody measured with tiny rulers. It's a conceptual radius. It's defined as the radius A you'd need so that the electron's calculated self-energy, one text like exactly, equals its known rest mass energy, 1c22.
So you work backwards from the known mass.
Sort of. You set one textlick, which depends on 1 or $2, equal to Miss Lady 22, and solve for $2. Calculating $2 gives a tangible number, something around $2.82 times 1013 centimeters. It's tiny, but it gives a scale.
So this 20 Lars is the size the electron would need to be, classically, for its mass to be entirely explained by its electric field energy.
Correct. And it's worth noting briefly, this calculated electromagnetic mass, it does behave correctly under special relativity. It increases with velocity by that familiar factor, $1 squared 1 v2c22. So that part seemed okay.
But now, let's get back to that factor of 2/3, because we have two different rules clashing, don't we?
We do. On one side, Einstein's famous equation, Win mc2 or $1 e ec22, mass is equivalent to total energy divided by c squared.
Okay. But on the other side, our derivation for the electromagnetic inertia, the mass from the field's momentum, gave us monopitch 2/2.
Exactly. There's a factor of 233 versus a factor of $1. We seem to be missing 1/3 of the expected inertial mass if we only consider the electromagnetic field's energy and momentum.
So the mass derived from the field's momentum doesn't match the mass derived from the field's energy using EMC to 2/2.
That's the critical conceptual chasm. That factor of 23, or sometimes people call it the 43 problem, when looking at momentum versus energy, it means the model isn't self-consistent with relativity. The electron, modeled this way as just a charged sphere, simply doesn't work relativistically.
Okay, so if the calculation of the field momentum comes up short, how did physicists try to fix this? How do you maintain consistency with relativity? This sounds like where things get really creative.
Highly inventive, yes,
Yeah.
to save the classical picture and also just to make the electron stable. Remember, all those bits of charge should be repelling each other, right? The thing should fly apart instantly.
Good point. Yeah, it needs something holding it together.
So physicists realized the electron couldn't be held together by electromagnetism alone. There had to be some other forces involved. Hypothetical non-electrical pressures, essentially, holding the charge distribution together. These became known as Poincaré stresses.
Poincaré stresses, and crucially, these weren't just needed for stability, they also had to fix the inertia problem, that factor of 23.
Exactly. That was the hope. To satisfy the relativistic requirement that total mass equals total energy divided by 2 magnitude 2, these Poincaré stresses had to contribute energy and momentum too. And it turns out they needed to contribute precisely the missing 1/3 of the energy mass equivalence. And because the electromagnetic energy is positive.
The binding energy from these stresses had to be negative.
Yes, the binding forces had to contribute negative internal energy and also negative momentum in just the right way to balance everything out. This really shows the immense conceptual difficulty. The classical electron wasn't just a simple charged sphere anymore. It became this carefully engineered, internally stressed system.
Held together by hypothetical forces designed specifically to cancel out the model's own mathematical inconsistencies. It sounds less like a fundamental particle and more like, well, a patch.
It does have that flavor, yes. And the problems didn't stop there. They got worse when you considered acceleration. This brings us to the idea of self-force and radiation resistance.
Okay, so what happens when the charged particle isn't just moving, but accelerating?
When it accelerates, things get even trickier. The force exerted by one part of the charge distribution on another part isn't balanced anymore. Why? Because the electromagnetic field takes time to travel from one part of the charge to another. There's a delay.
Ah, the speed of light limit. So if it's accelerating, the message from one side arrives a bit late at the other side.
Kind of like that. You can imagine the field line sort of lagging behind the acceleration. This lag creates a net force back on the particle itself, a self-force.
And this self-force, it opposes the acceleration, like a drag.
Exactly. It acts as a drag force opposing the acceleration. And this force is intimately connected to the energy the particle radiates away because it's accelerating. That's why it's often called radiation resistance.
So the particle kind of fights its own acceleration because of its own fields.
In a way, yes. And mathematically, when you calculate this self-force, it comes out as a series, an expansion. The first term in this series is proportional to the acceleration itself. And guess what? That term is precisely what gives us the electromagnetic mass, the 23 time we discussed earlier.
Okay, so the inertia part is in the first term. What about the next term?
The next term is proportional to the rate of change of acceleration, the third derivative of position. And that term corresponds exactly to the radiation resistance force, the energy loss.
Wow. So inertia and radiation damping are mathematically linked in this self-force calculation.
Yes, it tied inertia and energy loss together within a single framework of self-interaction, which is elegant in a way, but still built on that shaky foundation.
So bringing this all together, what's the verdict on classical physics here? The takeaway seems pretty unavoidable.
Absolutely. Classical electrodynamics, when you combine it with the idea of a rigid fundamental particle, it fundamentally fails. It leads to two major dead ends: the infinite self-energy for a point charge, and this factor discrepancy, the 23 or 43 problem, related to energy, momentum, and inertia.
And these weren't just small issues. These failures were so profound they triggered some really radical attempts to actually modify Maxwell's theory itself, right? People tried to fix the core equations.
They did. For instance, Born and Infeld tried a very complex approach. They proposed making Maxwell's equations nonlinear. The hope was that this nonlinearity would naturally cap the electric field strength near the particle, preventing it from going infinite at R0, and thus solving the infinite energy problem in a self-consistent way.
Complicated, but an attempt to stay classical-ish. And then there was Dirac's approach, which sounds much more out there.
Oh, Dirac was famously radical.
Yeah.
He proposed modifying the fundamental theory by introducing the concept of advanced waves. These are waves that mathematically propagate backward in time.
Backward in time, how does that even help?
It sounds bizarre, but mathematically it worked wonders. By allowing these advanced potentials, Dirac showed you could construct a theory where the infinite self-mass term perfectly canceled out.
So it allowed the radius A to finally go to zero without the energy blowing up.
Yes.
Oh.
And amazingly, this same modification also naturally incorporated the radiation resistance force term, the one proportional to this, without needing separate assumptions. It solved two major problems at once.
A mathematical triumph? Maybe, but at the cost of a pretty wild physical concept effects preceding their causes.
Indeed. It was a mathematically elegant solution achieved through a radical departure from standard physical intuition. There were other attempts too, like Bopp's theory using a non-local potential.
Non-local, meaning interactions aren't just at a single point.
Essentially, yes. It spread the interaction out slightly. This also managed to yield a finite, relativistically invariant mass for the electron. But again, it introduced its own conceptual complexities about point interactions. It just shows how difficult this problem really was.
So attempts were made to patch up classical electrodynamics. But maybe the deepest challenge to the whole idea of electromagnetic mass came from looking beyond the electron.
That's a crucial point. If the electron's mass is, let's say, partly or wholly electromagnetic, what about much heavier particles, like protons and neutrons in the nucleus? Where does their mass come from? We clearly need to go beyond just electricity and magnetism.
Right. We can look at, for instance, the small mass differences between charged and neutral particles that are otherwise very similar, like the neutron and the proton. They're almost the same mass, but not quite.
Exactly. The neutron is slightly heavier than the proton. That mass difference, delta M, is tiny, only about 1.3 MeV in energy units. That's a very small fraction of their total mass, which is around 940 MeVs.
So the difference caused by the proton's charge is just a tiny fraction of its total mass?
Precisely. You see similar small differences between charged and neutral pi mesons too. These small differences strongly suggest that electromagnetic effects, the self-energy of the charge, contribute only a tiny correction to the mass of these heavier particles, not the main source of their inertia.
So the bulk of the mass for protons, neutrons, pions, it must come from something else entirely.
Yes. It must be dominated by different kinds of fields, the fields associated with a strong nuclear force.
And this leads us naturally to the field theory developed by Yukawa, trying to explain that nuclear force.
Right. Yukawa had this brilliant idea. He theorized that the strong nuclear force, the glue holding the nucleus together, is mediated by exchanging particles. We now know these as pi mesons, or pions. And the force potential associated with this exchange, the Yukawa potential, has a very specific mathematical form.
How does it differ from the potential for electromagnetism, the Coulomb potential?
The Coulomb potential for the electric force just goes like 1 over A. It falls off relatively slowly, giving it infinite range. The Yukawa potential, however, is proportional to Weibo.
Okay, so it has the dollar tone, but it's multiplied by this exponential decay term, a mu.
Exactly, and that exponential term is the key. A mu causes the potential, and thus the force, to drop off extremely rapidly as the distance increases, much faster than normal dollars. This rapid decay explains why the nuclear force is so short-ranged. It basically only acts effectively inside the nucleus, unlike the electromagnetic source, which stretches out forever.
And the connection back to mass, that constant mu in the exponent.
That's the crucial insight we've been building towards. Yukawa showed that the constant nu in that decay term is directly related to the mass of the particle being exchanged to the mass of the pion in this case.
So the range of the force is linked to the mass of the force carrier.
Inversely related, yes. A more massive exchange particle leads to a shorter range force because that exponential decay is faster. The larger the mass, and thus quicker E mu lease, goes to zero. This was a profound confirmation of the principle that understanding mass requires field theories, and that different forces have different field quantas with different masses, determining their range and strength. It showed conclusively that we needed theories far beyond classical electrodynamics to understand mass itself.
Okay, let's try to recap this whole journey then. We started with what seemed like a simple idea. Calculate the energy in an electron's electric field. But that immediately led to the paradox of infinite energy for a point charge.
Right, which forced us to consider a finite size, leading to the concept of electromagnetic momentum and electromagnetic mass. But that ran straight into the 23-factor discrepancy with relativity.
Which then demanded these kind of ad hoc fixes, like Poincaré stresses non-electrical forces needed just to make the model stable and relativistically consistent.
And it triggered those radical, though ultimately incomplete attempts to actually change Maxwell's equations or the underlying physics, like Dirac's advanced waves or Born-Infeld theory.
But the final realization seems to be that even these fixes couldn't account for the mass of most particles. The small mass differences between charged and neutral particles and Yukawa's theory of the nuclear force.
Showed that most mass comes from other fields, like the strong nuclear field, mediated by massive particles like pions. The range of the force is tied to the mass of its carrier.
So the central insight seems to be that classical electrodynamics, in its ambitious attempt to maybe unify charge and mass, fundamentally breaks down at these small scales. These weren't just minor technical issues, they were deep conceptual failures that forced physicists to abandon the simple picture of a rigid particle.
Absolutely. They showed the necessity of thinking about particles in terms of fields, whether electromagnetic or nuclear, and that mass itself isn't some inherent mechanical property, but really an emergent property related to the energy stored within these fields and their incredibly complex interactions.
So, if this core idea holds that mass is fundamentally a property of fields, and yet even today our best quantum field theories still struggle to calculate the electron's mass perfectly without mathematical tricks like renormalization to handle that original infinite self-energy, it makes you wonder, what fundamental properties, what aspects of the structure and interaction of these basic charged particles like the electron might we still be missing? What piece of the puzzle is still not quite in place? Something for you, the listener, to perhaps mull over or explore on your own.